All right, 3.5, we're going to change gears just a little bit. We're going to actually be solving equations. We have not been solving equations. At best, we've been simplifying expressions, okay? Equations mean they have an equal sign, okay? So we've been simplifying expressions using trig identities, or we've been verifying identities. Those are the two things that we've been doing, simplifying expressions and verifying identities. But we're actually going to be solving some equations here. And so this is going to feel more like algebra, right? Where at the end you get something that says like x equals this, or maybe a theta equals this since we're working with angles. So it's going to feel kind of like that. So some basic strategies first for solving trigonometric equations. So we're going to decide if the equation is linear or quadratic. We do deal with linear equations and quadratic equations a little differently. So we kind of need to make sure that when we're looking at it, we recognize what we're looking at. Secondly, if only one trig function is present, we're going to solve the equation for the function. So like if there's a tangent and there's no other trig functions in there, we're going to get tangent all by itself, shift everything else, and we're going to move things around like that. But if there's like a tangent and a sine in there, that's not going to work. Okay? Third thing, if more than one trig function is present, we're going to rearrange the equation so that it equals 0. That's actually what you do with quadratics as well. You try to get everything on the same side and a 0 on the other side, and then we manipulate from there. So if we have more than one trig function present, that's what we're going to do. Everything on the same side, 0 on the other side. And then we set each factor equal to 0 and solve. That is how we deal with quadratics. Okay? And then number 4 is that we're going to try using identities to change the form of the equation. Sometimes they don't solve directly, right? It doesn't just say sine of theta and you solve for theta. Maybe it says sine of 2 theta. Now you got to solve for 2 theta, and there's some manipulation involved using these trig identities we've been working with. So all these identities that we've been working with, that page that I gave you back at the beginning of 3.1, are fair game to show up inside of trigonometric equations. Okay? So we need to see some examples. And the examples do have some differences in the way that the question is asked. So what I want you to take a look at here is that we're first just going to figure out whether or not this really is a solution. Okay, does it work? All right, so if it's a solution, it means you can take the value they give you. In this case, they're saying x is pi over 3. You can put it in for x, and you can see if it solves the equation. You can see if it works, if it's true. And we do this for algebra all the time. I mean, like that is exactly where we start with solving equations in algebra. We try to figure out, is this one really going to work? Is this one really going to work? Sometimes people want to do that, and it's called trial and error. And then some teacher says, we're not doing this by trial and error because that's going to take too long, right? Okay, but in this case, we've got one example we're trying to figure out if this works. So we're going to take the pi over 3, and we're going to plug it in for x. So we're going to figure out what is the tangent of pi over 3. And as we do this, we do need to be thinking of the unit circle, all right? You can check this on your calculator, but tangent of pi over 3, if it's irrational, is not going to give you back a number that's going to be easily determinable, okay? So we're going to double check real quick, figure out where we are at pi over 3. So at pi over 3, we are up here, right? This is pi over 3. It's equivalent to 60, if it helps you to think about that in terms of degrees. What is the ordered pair here at 60, or pi over 3? It's 1/2, and square root of 3 over 2. Cool. Oops. 2. There we go. And tangent is the same thing as what in terms of trig functions on these? Like, y over x. Yeah, it's y over x. So we're taking a look at this, and we're thinking, okay, I'm going to kind of write it over to the side, that this is y over x. So the y value here is square root of 3 over 2. And the x value is 1/2. Everybody good? I want to manipulate, simplify this, clean this up a little bit, and I can do that by multiplying the top and the bottom by 2. So on the top, when I have square root of 3 over 2 times 2, what will I get? Square root of 3. On the bottom, when I have 1/2 times 2, what will I get? That's just 1. So this, in fact, does equal the square root of 3, which is what we were checking to see if it works. It did work. So this is a solution. Does that make sense? So if it gives you a value and asks you if it's a solution, it's plug and chug. You're plugging it in and you're simplifying things out with the trig that you've learned to see if it works or if it doesn't. If this had said It not it said square root of 3, it had said equals square root of 2, the answer would be no, that it doesn't work, right? We would have gotten square root of 3 at the end. We would have compared that back to where we started with. We would have said, no, they're not the same thing, so it's not a solution. Does that make sense? Okay, these are isolated cases, right? Because most of the time we are not given something and just told to check and see if it works. We're asked to find something that works, which is a harder thing to do. So let's take a look at another example where we're asked to find something that works. Isaiah?
No, I'm thinking of the answer.
Okay, you're just thinking. Okay, cool. All right, so we have an equation here. This equation has how many trig functions in it? One. The only thing it has is sine. Okay? So, and it's linear. It's not sine squared. It's just plain old sine. So when we have one trig function, what we're going to do is we're going to try to get that trig function by itself and move everything else to the other side. Everybody good with that? Okay. So the first thing I might do is what? Think about some algebra skills. We haven't done a lot of algebra skills here. Subtract a 3, you bet. So we're going to start by subtracting a 3. So now I have 2 sine of x equals 1. Very good. Now what? Divide by 2. So now I have the sine of x equals 1/2. Okay, so we have to be careful. So Isaiah says that's a 2 spots, and that's partially correct. Take a look back at how it asked the question, though. Ooh, it wants us to find all the solutions. Now, pause for a moment and just take a look at number 3, if you've got the printout for this. What does number 3 ask us to do? What was it? On a specific interval, right? We're only supposed, when we get to number 3, it says we just want the answers on the interval 0 to 2 pi. This question doesn't say that. If this question said I only want the answers on the interval 0 to 2 pi, then we will have 2 answers. But because this says I want all solutions, we're going to have to do something a little bit different at the end of this problem, okay? So when I mentioned at the beginning of this one that the directions matter, they really will. The directions will change from, sort of problem set to problem set, and you need to pay attention and make sure that you're doing what those directions say. Okay, this is a following the directions exercise. We all struggle with that sometimes. Usually we just don't pay attention. That's what it is for me anyway. Happened on homework with my child last night. She got really mad at me because I didn't notice something in the directions. I wasn't being careful, okay? All right, so we're taking a look at this one. We are going to take a look at where this happens on the interval 0 to 2 pi to start with. I mean, that's where we have to begin regardless of whether we're doing this for 0 to 2 pi only or we're doing it for all. So we want to think about the unit circle. Let's start with where are sine values positive, because this is a positive 1/2. Which quadrants give me positive sine values? 1 and 2, you got it. So my answers are going to be in quadrants 1 and 2. Everybody good so far? Okay, where in quadrant 1 do I get a sine of 1/2? Okay, pi over 6. So we are working in radians. So this is at pi over 6. That's one of them. How about second quadrant? Somebody else. Hold tight. Jonas? Yep, it's at 5 pi over 6. It's this one right here. So all the way over here, we're at 5 pi over 6. Now, there's some 1/2s that show up in quadrants 3 and 4, but they're negative 1/2s, right? Okay, so we do have 4 places where I have something that looks like 1/2. I just want to make sure I get the sign right as well. Okay, so we've got 2 options so far. This x is going to equal, and I'm going to write this in a specific way, pi over 6. And I'm going to write this as equal to 5 pi over 6. And I'm writing them not beside each other on purpose. Please write them not beside each other. Because we have to indicate that we would be able to find all solutions, and this is only 2 of them. Well, if we go to the next one, we would have to go all the way around, right? We'd have to go all the way around to here. What would I have to do if I wanted to if I wanted to go all the way around again? We would have to add 2 pi, right? Going all the way around the circle is adding 2 pi. What if I wanted to go around the circle again? I add another 2 pi. And what if I want to do it again? I do another 2 pi. And I could keep doing this forever, right? So there are infinitely many solutions to this equation. And if you think about our graphs, that kind of makes sense. Our graphs have this infinite pattern, right? Like sines and cosines anyway, where they go up and down. And what we're looking for is we're looking for them to sort of cross through some horizontal line. And they're going to do that infinitely many times. So what happens and how we write that is that we write that we're going to do plus 2 pi right here. We'll do it on both of them. But this would only give me one more, right? And I want to be able to do this, forever. So I have to have a way to write that. So what we're going to do is we're going to write K or N. It might actually give you an option of what they want you to use when you're working with this in my math lab. I'm not sure. I don't care what you use. I'm going to use K. And then we have to say, what is K? Well, K is an integer. And I'll put it on both of them. If you wanted to put it at one final statement on the whole thing, that would be okay too. K is an integer. Not only can I add 2 pi and add another 2 pi and add another 2 pi and add another 2 pi, I could actually subtract them as well. I could go the other direction. That's why it's an integer and not just a whole number. Integers are positives and negatives. So I could add negative 2 pi, and I could add negative 4 pi, and negative 6 pi, and I would have other versions of the answer going the other direction.
Does that answer, like on tests, have to have K as an integer?
It will. If it asks the question in this fashion, yes, it will. Okay? So if the question asks for you finding, sorry about that, all solutions, like it says right here, then you're going to have something that looks like this. K is an integer, or N is an integer, whatever letter you want to use. It doesn't really matter at the end of it, and that's going to be multiplied by your 2 pi's. Okay. Now, the majority of them that we're going to work with aren't going to have that variety to them. They're going to look like what I'm about to do in number 3. But is everybody okay with that one? Okay. So what happens when we do problems like this one, find all the solutions to the equations. There's a typo on this one. It should say, does it say on your paper, on 0 to 2 pi? Okay, it just got left off the screen. All right, it should look like that on the interval 0 to 2 pi. So we're going to use this equation, but we're not going to have to do the 2k pi thing at the end, right? We're just going to find it on one unit circle interval, and we will be done. Now, there is only one trig function. It's just cotangent. And actually, it's already solved for it. It's linear. It's not squared, right? But it says 3x. It doesn't say, just x. And that is going to create a difference in how we solve this problem. You might also notice it doesn't say 2x. If it said cotangent of 2x, I have some double angle formulas that I could put into play here, right? If you go back, we have some that they're all talking about, like what is sine of 2x and what is cosine of 2x. I could do something where I've got cotangent of 2x. This isn't 2, it's 3. And you can't just change a 2 into a 3 and think it's going to work the same way. It won't. So we will have to deal with this in a different way. So let me show you what this looks like. First, we are going to think about our unit circle, and we're going to think about where we get cotangent values that are going to be equal to square root 3. Now that's harder to think about than sine values and cosine values, isn't it? We have sine values and cosine values, and they're actually like the ordered pair components. They're the x or the y, and cotangent's not like that. Cotangent, if you'll remember, is y over x. I didn't write that right. X over y, so I meant to write x over y. Let's get it in the right order. X over y. So I have to think about places on my unit circle where the x value divided by the y value is actually equal to square root of 3. Now, it's clearly going to have something with a square root of 3's in it, right? There's two different angles. This one's positive as well. Let's talk about where cotangent is positive. So cotangent's positive in quadrant 1. Do you remember where else is cotangent's positive? 3 is right. Yeah, it's 3. So let me remind you of how we can think about it, at least one way to think about it. A smart trig class, ACT. So T down here, tangent. This quadrant 3 is tangent and it's reciprocal. Tangent's reciprocal is cotangent. So quadrant 1 and quadrant 3 have tangent values and cotangent values that are positive. So we are in quadrants 1 and 3. So we need to be thinking, are we down here or are we up here? It's one of the two. Right? It's either pi over 6 or pi over 3. Does everybody understand that makes sense? Because those are the two places where we have ordered pairs that have a square root of 3 in it. So let me write them out and see if we can figure out which one's which. So this one's square root 3 over 2, 1/2. And this one up here is 1/2, and then square root 3 over 2. Which of those two, when divided, will give me square root 3? I have to divide x by y. That's not a very good color. Which one?
Pi over 3.
Pi over 3. If I divide x by y, I'm going to get square root of 3. Okay, let's try it. So if I divide x, which is 1/2, divided by square root of 3 over 2, am I going to get square root of 3? Yeah, this is going to give me 1 over square root of 3, right? Everybody okay with that? If I do this one down here, and I have square root of 3 over 2 divided by 1/2, and I multiply by my 2, like I did on the previous example, I'm going to get square root of 3 on this one. Okay, so it's actually the pi over 6 angle. Okay, that's not a very good 6, but here we go. Pi over 6. It's going to be at pi over 6. That's in quadrant 1. Do you have a question?
So for the square root, or for the cotangent, is it the same value as the tangent? Because when you flip that, like, is it the same value?
No, because if you flip square root of 3, like if you do square root of 3 and you do 1 over square root of 3, and you were to simplify it,
So 3 over 3.
you'll get square root of 3 over 3. And hang on. Yeah, it's similar, right? You'll still have a square root of 3 involved, but it's not equal to square root of 3. So this one does not equal square root of 3, right?
Yeah.
Okay, so pi over 6. Are we okay that pi over 6 works? Okay, so one of our angles over here is going to say pi over 6. What's the corresponding angle in quadrant 3 that will work then?
7 pi over 6.
It'll be 7 pi over 6, right? The pi over 6 angle is still the one we're working with down here. So it is 7 pi over 6. Now here's the deal. That's what the angle equals. So we could divide these both by 3, right? And we will in a moment to get our angle. But the problem is that I could actually have a bigger value that I divide by 3 and still be within the interval 0 to 2 pi.
The degrees.
Are you guys with me? What's that?
Is it the degrees?
This is in radians.
Oh.
Yeah, we're in radians. So I'm going to show you what's going to happen. This is the one we would have gotten originally, right? If we just went 0 to 2 pi using our unit circle as normal, we get these two values. Everybody get that?
Yep.
Okay, do you remember on the last one we added the 2 pi and we added the 2 pi and we added the 2, like we talked about how we could just keep adding 2 pi? Because this is a triple angle, I'm going to need to have 3 pairs of angles that work. Because when I divide by 3, it's going to change things to be between 0 and 2 pi. Okay, so this is one set. I need to shift this over. If I take these and I add 2 pi, to each of them, what am I going to get? In other words, what is pi over 6 plus 2 pi? $13. Yeah, it's 13 pi over 6. Okay, so what I'm asking you to do is to do 1 over 6 plus 2, right? If I've got pi over 6 plus 2 pi, that's 1 over 6 plus 2. Your calculator will do that for you if you would like, and to turn it back into a fraction. It is 13 over 6. 13 pi over 6. We're going to do the same thing with 7. So if I have 7 over 6 plus 2, I'm at 19 pi over 6. Okay, so this is a second set, but I've got a triple angle. This is 3x I'm going to solve for, a triple angle. So we need to do one more set. I need to add 2 pi one more time. Whoa. There we go. You add 2 pi one more time. So what happens when I add 13 over 6 plus 2? What is it?
25.
It is 25 pi over 6. And I need to do it one more time beyond that. Hang on. What did we have left over? We had 19. If we do 19 over 6 plus 2, what do we get? 31 pi over 6. Okay, there's 3 sets. The reason there's 3 sets is because we have a 3x. The reason there's 3 sets is because we have a 3x. Write that in your notes. Because if you look back at this later and you're going to be like, why did we keep going? I thought we were done. And all these angles that I'm getting are too big, right? 13 over 6 is bigger than 2 pi. Why in the world is this one of my solutions? Well, it's not. We're not finished. Our last step on this problem then is to take this over 3 part at the beginning and to multiply by its reciprocal. And we're going to do that to every single number that we just wrote. Now, that looks like it's a big deal, but don't make it a big deal. You're just going to multiply all the denominators by 3, right? All the denominators are 6 right now. So if I multiply them all by 3, what do I get? 18. All I'm doing is writing the exact same expression that I had before, but changing the denominators to 18. I'm going to have to simplify a couple of them, but it's not that bad of a process because the numbers are all the same on the bottom. So we're going to get pi over 18, 7 pi over 18, 13 pi over 18, 19 pi over 18, 25 pi, over 18, and 31 pi over 18. And we should pause and ask ourselves, do any of those simplify? And actually, now that I'm looking at them, I don't think any of them do. None of those numerators are divisible by 3, are they? They're all odds. Well, not that they're just odds, but they're all values that don't divide by 3. So this right here is where my answer would stop. And if you're sure, if you're still thinking, I still don't know why we did that, take a second. I'd like for you to divide 31 by 18. Just grab your calculator. What is 31 by 18? You can give me some sort of decimals, fine. What do you get when we divide 31 by 18? Simon's going to get it for us. Oh, somebody else had it? What do you have, Terry? 1.7222. Is that bigger than 2? Nope, it's smaller than 2. Every single one of those, ignore the pi part, are going to be between 0 and 2. So when we put on the pi, they're going to be between 0 pi and 2 pi. And if we try to go one more beyond this, right, if I added another 2 pi to something, it's going to be bigger than 2. So I have 3 sets of angles because I have 3x. Okay? And this is a great place for us to stop.